all this talk about period and frequency has got me thinking about marching bands. Why not? Sure. And I know that there are some people in this room, probably. How many people in this room are in a marching band? Yeah. All right. Two people, two marching band people. Nice. All right. So I know that we're in a big marching band city here. And we do competitions. So we know about this kind of thing. So this person is somebody, let's pretend that they're in a marching band. And everybody that's ever seen a marching band, there's the person that has the baton at the front, right? What's that person's role really? You guys know? Other than make things look good. Aren't they actually a human metronome? Essentially, right? Traditionally, that's the role. Okay, so this person at the front keeps the pace. They're supposed to be like a human metronome. What that means is that they're supposed to raise and lower a baton at a uniform rate. Whether that really happens in practice with today's modern marching bands and modern marching band sciences, that was the role originally. What's more is the marching bands of today are also based on old colonial armies of the past. You guys probably know that, right? Like the bright red uniforms and the beautiful blue outfits and things like that. That should tell us that there's something that maybe looks a little bit military here. And so this person's carrying a baton, but it also looks suspiciously like it might be a rifle from olden times British days or something like that. And that's why this illustration gets used. This illustration's been used for about 100 years. Because people can picture marching bands. People can picture like a military parade or something like that. And there's always been somebody in the front keeping time. The reason there's somebody keeping time is because everybody in the band has to be in synchronized steps. Can you just picture what I'm saying? Here are these marching steps. Thunder, 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 all together. And sometimes we still see videos today of militaries that march in unison like that. This was really important historically. Everybody had to march together because if you didn't, you'd be tripping over the people in front of you. You need to make sure everybody's moving together. Not only that, but if everybody steps so that their steps land at the same time, intimidation. Agreed?
Yeah.
That's intimidating, for sure. But that's not what I want to focus on right now. I just want to have an image for where we might see this. This person here is walking. And this person starts off walking on pavement. Picture that. But as they transition, can you imagine they get down to the local beach? As they get down to the local beach, are they going to be going as fast or slower or faster? Yeah, they will. They'll walk slower on the beach. Anybody who's walked on the beach knows it's harder to walk on the beach than it is on the pavement, right? Now, at the same time, since this person's like a human metronome, what they're doing is they're raising and lowering their baton. Boom, 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 at a constant frequency. Cool? That keeps pace. But they might be raising and lowering it at a constant frequency, but notice their feet are slower here. So even though the up and down motion is constant, the side-to-side motion is slowed down here. What that means for the waveform that would be traced out by their baton is that it becomes more bunched up here. You guys picture what I'm saying now? Like if I could have like a video of this thing, remember, paper doesn't animate very well. So this is my attempt at animating paper. If this person marched across the page, their baton would go up, down, up, down, up, down, up, down. Their horizontal motion would be the same speed the whole time, which would mean that the wave would be more compressed over here. All cool? All right, so let's add some information onto this. I want to say that the period of this up-down motion is 2.00 seconds. The speed, now I'm going to call it speed 1 because I'm going to say that this is walking surface 1. And I would call this walking surface 2. The person's speed on walking surface 1 is 2.00 meters per second. Yeah, keep it nice and simple, yeah? When we get over to here, the period stays the same because they are still the same rhythm keeper. 2.00 seconds. But we said on the beach it's slower, so V2 is slower. I'm going to make the numbers nice and simple, 1.00 meters per second. We're going slower. I'll make a qualitative note. V2, slower. Another qualitative note, V1, faster. Okay? And another little note to ourselves, period stays the same throughout. Now, what happens to the wavelengths? Yeah? Smaller wavelengths. Smaller wavelength. I'm going to say lower or smaller wavelength because depending on who you're talking to, they might use either word, okay? I use smaller personally. These guys here are longer wavelengths or larger wavelengths. Okay, we're just labeling up the stuff that we know. So when I go from one speed region to another speed region, my wavelength can change. And by the way, we don't just call them speed regions. In optics, we call them media, right? One medium to another. So when we go from one medium to another, the speed changes. This is actually one of the reasons why refraction occurs, but that's not the aspect that we're talking about right now. But the speed changes from one medium to another. If I wanted to make measurements on a grid, look, there's my lambda. It's a small lambda. There's my lambda. I'm just choosing identical points, the distance from trough to trough in this case. That's a large lambda. So we can get a little bit more quantitative about this. Now, if we did want to get more quantitative about it, I want to introduce an equation, one that we know already. Speed is equal to distance over time. That's something we definitely know. When it comes to waves, though, let's just say in waves, we don't talk about it in terms of speed equals distance over time. We talk about the speed of a wave as being how far it travels for one complete wave cycle over the amount of time it takes to produce one complete wave cycle. So how far does it travel for one complete wave cycle? Well, that's lambda. How long does it take to produce one complete wave cycle? That's period. These are things we've been talking about today. I'll put a box around that. And I would call that equation 1. Equation 2 is that period is equal to 1 divided by frequency. I'll call that equation 2. Period is equal to 1 over f. And if I sub 2 into 1, again, a little bit of algebraic gymnastics, I end up getting v is equal to lambda times f. Speed of a wave is equal to its wavelength times the frequency of the source. In this case, the source is this person in the marching band. But the wavelength changes. Notice that the person that's in the marching band does not change his frequency, does not change the rate at which that baton goes up and down. That frequency is a characteristic of the wave. The wavelength changes when you go from one medium to another. I'm going to kind of sell on this idea. I feel like we didn't sell this idea mathematically in grade 10 for most people, right? So I want to make sure that everybody's got this idea. And it's even got a name. It's called the universal wave equation. Called the universal wave equation. And actually, it's just like the wave case version of speed equals distance over time, right? Universal wave equation. That's all. Now, as a side note, since we did kind of talk about this when we were doing grade 10 optics, in optics, if you wanted to hang your hat on some previous knowledge, we actually say c is equal to lambda f, where c is the speed of light, which happens to be like 300 million meters per second, 3 times 10 to the power of 8 meters per second. That's the speed of light in a vacuum. But c equals lambda f, where c is speed of light, is the exact same equation that we use in optics that we would use in sound for the universal wave equation. It just happens to be that it's a different kind of wave. It's a light wave instead of a sound wave, that's all, or a water wave. And and it's 3 times 10 to the power of 8 meters per second. Now, do you have to know that little red fact that I threw in there? No, you do not. Okay, I just want to make sure that it's clear that we're like, yeah, we're spinning an interwoven web. Okay, by grade 12, you care about that again. We won't care about it for now. All right, so I got this question. Find the speed of a wave with a frequency of 4 hertz and a wavelength of 2.5 meters. All right, well, wave frequency. Our frequency, 4.0 hertz. Wavelength, 2.5 meters. All right, well, the speed is v equals lambda f. Now, as I sub these values in, it's 2.5 meters times 4.0 hertz. And people that are unit purists are going to say, wait a minute, that's going to end up being a coefficient of 10, but the units are going to be meter hertz. What the heck is a meter hertz? Well, a meter hertz if it hits you in the head, but a meter times a hertz, remember what a hertz is. A hertz is a 1 over seconds is. Right? So it makes sense to us that the speed's still going to be in meters per second. Nobody writes them as meter hertz. Everybody writes them as meters per second because when you're at this stage of the learning process, you should be able to make this connection. Okay? Yes?
What happens if I do write down as meter hertz?
If you write it as a meter hertz, I'm going to take off communication marks. All right. Nobody writes meter hertz. Right? I'll put it in writing. Not meter hertz. Exclamation mark. Okay? Nobody does that.
I'm going to tell Rafi if he gets extra marks.
No. Don't tell anybody any nastiness. All right. As a side note, when we did talk about refraction being caused by changes in wave or changes of speed, check this out. Can you guys see that if this is a wave, see these are wave fronts that are traveling towards a change in media? If this is the fast medium, notice that the wavelengths, I'll bring the other picture on. In the fast medium, notice that the wavelengths are spread out. The wave fronts are spread out. In the slow medium, the wave fronts are close together, just like these peaks are close together. So it's slowed down. The reason that it changes direction in refraction is because the direction of wave travel, this vector here, is always perpendicular to the wave fronts. See how it's also perpendicular to the wave fronts down here? And the only way for the waves to get shorter and not have there be a break in the wave fronts when it changes from one interface to another interface, the only way for that to happen is for the wave fronts to go angled like this. And if we want to talk about the geometry around that some more later on, we absolutely can. But this is really, believe it or not, this is the math that's the foundation for why refraction happens. It's just not the direction we're going to branch off into right now. We're going to go more towards some other stuff. But again, it still supports what we did earlier on in younger grades.